Hello and welcome to Chapter 7. This chapter is going to deal with applications of integration. And looking at 7.1 today, we're going to be dealing specifically with the area of a region between two curves. The objectives of this section are going to be to find the area of a region between two curves, as well as between two intersecting curves, and to describe the integration as an accumulation process. And the first thing we're going to look at is the area of a region between two curves. If you think back when we first started talking about integration, we mentioned that integration dealt with the area under a curve. We can actually apply that thought to the concept of the area between two curves. Now, if you look at these two functions here, we have function f, which is this curve, and function g, which is here in the light gray. Both of these functions, we're going to look at the area in between the interval from A to interval B. And if you think about what we've learned so far, we've actually learned that if I want to go and find the area underneath the curve, I would just integrate function f. So if I want to find the area in this region here underneath function f from A to B, I would just integrate that curve. Well, now let's say I want to find the area under the curve of region G. I can go ahead and come in and integrate and find this area. Now, if I want to find the area of the region between the two curves, all I have to do is find the area underneath F and the area underneath G and subtract the two. And if you look at these graphs here, that's actually what they show you. They show you that if you want to find the area in this region right here, we're going to actually integrate function f, which is the upper function. We're going to integrate to find the area underneath function g, which is the bottom or the lower function, and then the area is going to be that overlapping region, or the difference. In a nutshell, what we are really doing when we're integrating between these two curves is we're kind of creating a rectangle of some width, and we're going to call that width. Now, your book is going to use x sub I. It's also going to call it delta x, and I do apologize here in the presentation that the delta x's didn't transfer over properly. But anyways, we have this rectangle that has a constant width. Every rectangle that I take within this region is going to have some delta x width. Now, we know that the area of a rectangle is equal to length times your width. So if I know that my width is equal to delta x, I now have to find my length, which is going to be essentially the height. And to find the height, you're going to take your highest function, or in this case that's function f, and you're going to subtract that, or subtract the other function, or the lowest function, which is g. So you end up with a is equal to function f minus function g times your delta x. By adding up all of the areas of these rectangles that we are essentially going to be creating, and as n is approaching infinity, we're going to take this limit, and you'll see that we're going to approach this area of the region underneath the curve. Now, we actually have a property that says the area of a region between two curves is really given by the integral from A to B of your functions f of x minus g of x times dx, which is the change in x. And that's actually what we just proved out on the last slide. Now, these representative rectangles that we drew, that we're actually adding up to find our area, we can actually do these in two ways. One, we can do it with a vertical rectangle, which is what we just previously did. And what that does is that implies that we're taking integration with respect to x. Now sometimes, and we'll actually do an example later on, where it's more appropriate to use a horizontal rectangle, and if we do that, then we're going to be implying that we're integrating with respect to y. And like I said, we'll do an example here in a few minutes regarding that. Now let's go and look at example 1. It says, find the area of the region bounded by the graphs of f of x equals x squared plus 2, g of x equals a negative x equals 0, and x equals 1. In this case, we're actually given what the graph looks like. If you're not given, I would highly suggest that you at least sketch it out so you kind of know what you're looking at. But as you can see, we're trying to find the area of the region from the y-axis. It goes down the graph of g of x equals a negative x, over to the line x equals 1, and then underneath the curve, f of x equals x squared plus 2. If I go in and I draw my rectangle, as is given right here, I have a vertical rectangle, so that tells me that I'm integrating with respect to x, because I see that I'm going to have a change in x, which is going to be right here, of dx or delta x. And then I have to go and I have to calculate the height. And I'm going to find my height by taking my upper curve and subtracting my lower curve from that. So I end up taking f of x and subtracting g of x from that. So if I know my area is equal to f of x minus g of x, I'm going to go in and plug in my functions. So I know that f of x is equal to x squared plus 2, and I'm going to be subtracting g of x, which is a negative x. And this is all going to be multiplied, because remember this right here is really the height. I'm going to multiply all of this by my delta x, or my width. So if I simplify, I end up with x squared. Now this minus a negative x is really going to become plus x, and I still have plus 2 times the change in x, which is dx. Now to actually go and find the area, I'm going to integrate both sides, or I'm sorry, just integrate. So when I integrate this, I'm going to have to put my boundaries, and I know that my boundaries with respect to x are going from 0 to 1, so I'm going to include those from 0 to 1, and I'm going to integrate x squared plus x plus 2. So when I integrate x squared, I end up with x cubed divided by 3 plus x squared divided by 2 plus 2x, and I'm going to be evaluating that function from 0 to 1. The next thing we're going to want to look at is the area of a region between intersecting curves. Now, in the previous example, our graphs did not intersect, and our values of a and b, which are upper and lower bounds of integration, they were actually given to us because the graph told us that we were going from x equals 0 to x equals 1. Now, that's not always the case. In the more typical case would be that we're given a graph, one, that intersects at least once, if not more, and two, that we're going to have to actually calculate our values for a and b. So let's look at example 2, and in this case it says find the area of the region bounded by the graphs of f of x equals 2 minus x squared and g of x equals x. Again, we're given the sketch curve, but in the case that you weren't, go ahead and sketch it out. Again, if I come in here, I want to do a vertical rectangle because this is going to be hitting both functions. So when I go to find my area, I know that my area of a rectangle is going to be equal to my height, which in this case is this distance here. And I see that my upper function is still my f of x function. So I'm going to have f of x minus g of x, and I'm going to multiply that by my change in x, or my delta x here. So delta x. So if I go in and I plug in everything I know, my area is equal to f of x, which is 2 minus x squared, minus g of x, which is x, times delta x. This is going to give me, if I write it in standard form, negative x squared minus x plus 2 times delta x. And to solve and actually find the area, I'm going to go ahead and integrate. And this time, I have to find out what these points of intersection are, because I see I have a point of intersection here and a point of intersection here. Now to find those, I'm actually going to set my two functions equal to one another. So I'm going to go 2 minus x squared equals x. I'm going to get positive values of x squared, so I'm going to move my x squared and my 2 over and get 0 is equal to x squared plus x minus 2. And from factoring, I see that I can go x plus 2 times x minus 1. And this is going to give me a point of intersection at x equals a negative 2 and a positive 1. And if we look back at our graph, I think that's what you'll see. You'll see that we have this negative 2 here, and we have a positive 1 here. So now what I'm going to do is I'm going to take those points of intersection, and because I drew a vertical rectangle and I'm integrating with respect to x, I'm going to take this negative 2 and this 1 and plug them in for my boundaries of integration. So I have negative 2 to 1. So when I integrate this, I really end up with the integral from negative 2 to 1 of a negative x squared minus x plus 2 times dx. So to solve, when I integrate, I end up with a negative x cubed divided by 3 minus x squared divided by 2 plus 2x, and I'm going to be integrating this from a negative 2 to 1. And when I go ahead and I plug in my value of 1, and then take that answer and subtract that function evaluated at a negative 2, I ended up with 9/2 for the area between those two curves. If you don't remember the steps of the integration, please come and see me. Now sometimes we run into the case where two curves are going to intersect more than once on each end. And if that's the case, then what we need to do is we need to, 1, find all the points of intersection, and then 2, determine which curve is going to be above on each interval, because that's going to matter the order in which we have to subtract. So let's look at example 3 that says find the area of the region bounded by the graphs of f of x equals 3x cubed minus x squared minus 10x, and g of x equals a negative x squared plus 2x. If you look over here to the right, you can see that we have it graphed. And if you notice this time, I have more than 2 points of intersection. I have one here, and one here. So I'm going to start out by finding those points of intersection. And to do that, I'm just going to take my two functions and I'm going to set them equal to one another. So I have 3x cubed minus x squared minus 10x. Oops, I left the x out. Let me erase that. So minus 10x equals a negative x squared plus 2x. So when I move my 2x over and I move my x squared over, I end up with 3x cubed minus 12x equals 0. Well, I notice that both of these terms have a 3x in them, so I can factor a 3x out, and we're left with x squared minus 4. I know that x squared minus 4 is a difference of two perfect squares, so I can actually simplify that down into 3x times x minus 2 and x plus 2. So my points of intersection then are going to occur when x is equal to 0, 2, and a negative 2, which if we look at our graph, we'll see that our points do actually occur at all those points of intersection. The next thing I'm going to do is I need to take a look on my intervals. I see I'm going from 0 to negative 2, and then negative 2 to 0, and then from 0 to 2. So let's put these in order from least to greatest. So I'm going from negative 2 to 0, and then from 0 to 2. So I need to look at my intervals and see what function is greater than the other function, or which one's less than. And if I look in this interval from negative 2 to 0, I see that my function of f of x is still greater than g of x. However, when I come over to the second interval from 0 to a positive 2, I see now that g of x is greater. So I need to take the greater function and subtract the one that is lesser from that. The other thing I do is I need to make sure that when I'm integrating, I'm including the correct boundaries on my integration. Now again, before I do this, if I go in and I draw a rectangle, I see that I can draw a vertical rectangle and hit both of my curves. So I'm going to calculate my area by taking the integral. In this case, I'm looking from a -2 to 0. And we said that f of x was greater, so I'm going to take my function f of x, which was 3x cubed minus x squared minus 10x, and I'm going to subtract my g of x curve, which was a -x squared plus 2x, and I'm going to multiply that by d of x, because all of this here is the height of my rectangle, and the dx was my width. So now if I simplify, and I'm sorry, this was for the first interval. Now I have to go and do the same thing for the second interval, so I'm going to add that to the interval from 0 to 2. And now I said that g of x was actually greater, so I'm going to start out with a -x squared plus 2 of x, and I'm going to be subtracting 3x cubed, minus x squared minus 10x, and then multiplying this whole thing by dx so that I can find my area. So now if we go through and we simplify everything, I have the integral from a -2 to 0 of 3x cubed. I have a negative x squared here, so that's going to become positive x squared with this is going to give me 0x squared, and I have a negative positive 2x, which is going to give me a negative 2x, plus the already negative 10x is going to give me minus 12x. And this is dx. Plus the integral from 0 to 2, and I'm going to go through the same process of simplifying, except now I'm going to have a -3x cubed. My x squared terms I see are going to cancel, and I have a negative 10x that's being subtracted, so that's going to become a positive, so this is going to become plus 12x dx. So now I'm going to go ahead and integrate everything, and when I do that, we see that we have 3x to the 4th divided by 4 minus 6x squared. This is going to be evaluated from -2 to 0, and then I'm going to take that and add it to a -3x to the 4th divided by 4 plus 6x squared, and this is going to be evaluated from 0 to 2. Now when I plug all my values in, what I ended up with was a negative, let me erase it out of here. I have a negative outside, and then 12 minus 24 plus a -12 plus 24. And when I simplified all of that, I got a positive 24. And this then is my final answer. Now, our final example is going to be to find the area of the region bound by the graphs x equals 3 minus y squared and x equals y plus 1. When looking at this graph, the biggest difference you'll see is that all of my other functions before, I was able to come in and draw a vertical rectangle, and I could hit both my f and g functions. I can do that up to a certain point. As long as anything between -1 and 2 on my graph, I will hit both my functions f and g. But once I get over into this region, when I draw a vertical rectangle, I'm no longer interacting between f and g, but I'm actually interacting with just g by itself. So I can do this process. I'm just going to have to break up and do two separate integrals since my upper boundaries have changed. That's why it's actually, in this case, more practical to go ahead and use the horizontal rectangles and integrate with respect to y instead. Now, the process is still the same. I'm still going to find my points of intersection, and I'm going to find my points of intersection by setting my two equations equal to one another. So I have 3 minus y squared equals y plus 1. I want to solve and I want a positive y squared, so I'm going to move the y squared over to the other side as well as a 3. So I end up with 0 equals y squared plus 1. A negative 3 plus 1 is actually going to give me, y squared plus y minus 2. Now I can go ahead and factor, and I see that I'm going to end up with a y plus 2 and a y minus 1 is equal to 0. So this tells me that y is equal to a negative 2 and a positive 1. So let me fix that, sorry. Now, because I am integrating with respect to y, because of the horizontal rectangle, I have to think about what I'm really doing when I'm finding my area. Now, we said the area was equal to the integral of, I wanted the length times my width. Well, in this case, the height times my width. In this case, my height is not changing. This is going to be your delta y, which they've listed right here on the graph. Now, my width, this is where the change is occurring. And my width is going to be the difference between my f and g functions. So, because I have my g function is over here, I'm going to subtract my f function from my g function. So I'm going to end up with 3 minus y squared minus function f, which was y plus 1. I'm no longer integrating with respect to x. I'm actually going to integrate with respect to y, so I have dy, and my limits of integration are no longer with respect to x either. So I have to plug in those y values that I just calculated in for my upper and lower bounds. So I'm going to go from negative 2 to 1. And now the process is the same. I now have an integral with upper and lower limits, and I'm going to go ahead and simplify so that I can go ahead and fully integrate. So this is going to give me the integral from a negative 2 to 1 of a negative y squared. I see that I have a minus y negative on top of a multiplied by a positive is going to give me a negative 1 plus 3 becomes plus 2 dy. So now when I integrate, this is going to give me, a negative y cubed divided by 3 minus y squared divided by 2 plus 2y, and I'm evaluating that from a negative 2 to a positive 1. Now when I plug negative 2 and 1 in and do my subtraction, I see that my area was actually equal to 9/2. And example 4 now concludes section 7.1. So we'll see you in 7.2.